All right, so welcome back to the online portion of the course. Today we're going to talk about text data mining and more specifically on word embeddings. Because if you know how to encode those words into a vector, just like for the case of graph data modality, we should be able to do a lot of data mining tasks on the text. So far in this course, we've mostly focused on structured data such as tables, graphs and time series. So in those type of cases, the features are explicitly defined. In this lecture, we will switch to text, and here the meaning is implicit. So therefore, we really need to learn from the usage of the text rather than be given directly the feature vectors from our data. So the core question we should really ask today is how can we represent the words in a mathematical format so that their meaning and relationships are being preserved? Okay, so how do we measure similarity between words? For example, a car and an auto, or understand why car is a car, the word car is related to another word, gasoline, right? So a car and auto are more synonymous, so therefore they are semantically similar versus a car and gasoline, which are semantically related. But they are not necessarily semantically similar. So I guess in today's online portion, we'll start with early approaches based on linguistics, and then we're gonna move to distributional semantic models. And here, those umbrella of methods really learn from the meaning of the word co-occurrence in some large corpora of documents. So it will naturally leads us to the word embeddings, which we will add at the end of today's lecture. And here the idea is that words are represented as dense vectors in a continuous space. And that's what most of the modern NLP systems choose underneath their algorithms. So I guess we'll start first with some terminologies. So the term word embeddings comes from deep learning community, but the idea itself is really much older. So in fact, different communities use different names for the same core concept. So word embedding, typically used for deep learning or NLP communities. We also have distributional semantic models, DSM, typically used by the computational linguistics community. And other words which also are used for meaning the same exact thing are semantic vector space, word space, distributed representations. So all these words are really used interchangeably. They all mean representing the words in a vector format such that the semantic meaning is captured by some geometry, right? Just like we said before, if you have a vector representation of the word, then I can use distance, metrics, angles, directions, cosines to really measure the distance between those vectors. So the distinction is between word similarity and word relatedness is really important. I guess let's first start with the word similarity here. So word similarity simply means that those words are almost synonymous, right? For example, boat and sheep, car and cycle. Well, here they're kind of related. Car and automobile could be a near synonymous word, so therefore they are semantically similar. Now, on the other hand, word relatedness are words that are connected in meaning, but they are not interchangeable. So that's the idea. So we can say boat is kind of related to water. The car and gasoline are both related to each other, but they're not interchangeable here. So the similarity simply means that they have the same role. Well, the relatedness simply means that they're connected somehow to some topic or by some usage. That's the difference between the two. Okay, so word similarity is kind of like the building block for many tasks. So some tasks are document classification, document clustering, and here I mean that if someone just gave me a bunch of documents or journal newspapers, right, and tells me to without even learning the language in them, to classify them or to cluster them by grouping them into the same themes, then I should be able to do so if I know how to encode those vectors based on their distribution and their context, right? Um, some other tasks are the information retrieval, and you can imagine that's what the search engines are doing here. So they retrieve the most related information for based on our query. So language modeling, question answering, and even plagiat detection, right? So plagiat detection simply means that I would like to find some longest common subsequence across a corpus of documents that I have in my training set. So if your word representation is bad, everything downstream will suffer. I think that goes without saying. And there are really two major families of similarity methods. So when we talk about word embedding, we talk about the very first or most naive approaches are thesaurus based algorithms. Here, thesaurus based algorithms, they use a human linguistic resource like WordNet, a graph that we're going to see in the next slides. And here, the first category of methods, they really ask the question of, are two words close in hierarchy? If they're close in hierarchy, they simply mean that this simply means that they are similar. So similarity is based on where they fall in terms of the depth of this word net tree. And also the second one is, do their definition overlap? So that's the second question that thesaurus-based methods are basing their approach on. The second category of methods are the more modern approaches, and the one that we're going to focus on mostly in the text mining, in the text mining portion. So distributional methods are really learning from raw text data, and the core question that they ask is, does two words appear in the similar context? If they do appear in similar context, then it simply means that, well, they must be similar. They must be semantically similar. So this is the idea behind a lots of modern embeddings methods, and the one that are mostly used as well, such as the word2vec, glove, fast text, etc. So all the modern ones are based on distributional method approaches. All right, so let's start with the first category, thesaurus-based similarity here. So a thesaurus-based approach is based on this nice data structure, which you can see on the bottom right of this slide. So this is known as a word net. A word net is nothing but a tree where the nodes are have children nodes which are less common, and the root nodes and parent nodes are way more generic terms in our word net. So the words are nodes, and this is known as a hypernym graph, or also known as an is-a graph, right? Because the book here, if you look at the root node here, or the central node, we can say that the book is a rule book, or is a ledger, or is a play script here, which are the direct children node that we can that is related directly to the book node here. So the similarity is based on the distance, right? And when we talk about distance from the word net, this is an example, or a small screenshot of from the English word net here, of standard, medium, exchange, scale, etc., all the way to the leaf nodes. So similarity in the word net is typically measured based on the concept of the sim path, or the path length, if you wish. So here the similarity path between two concepts C1 and C2 is equal to 1 over the path length between C1 and C2. If you look at the example of nickel and coin, right, we assume that the path length between the child and the direct parent is always going to be 2, And all the other hops that are not direct parents are only a cost of one, right? So therefore here the path length between nickel and coin is equal to 2 because nickel is a direct child of coin. And therefore the sim path between nickel and coin is equal 1/2 or which is also 0.5. Well, the same thing for the sympath between fund and budget. So the fund and budget are only one hop away from each other. But because fund is the direct parent of budget, then the path length of fund to budget is equal to 2. So therefore here, the sympath between fund and budget is 0.5. So we can say that nickel and coin are equally similar to the fund and budget because of their position in the hierarchy. They are both a direct child to their parents, and therefore they are equally similar to each other. Now let's look at the last example that we have in the slide. So the same path between nickel and currency, which is a little bit far away in the hierarchy, so is equal to 1 over the path length between nickel and currency. So the nickel to coin, in order to go from nickel in order to reach the currency, which is the great parent in the tree, we need to reach first to coin, which is which has a 2 as being the weight. And from coin to coinage, we add a 1. And then from coinage to currency, we add 1, right? Because these are not direct parents to the word, the first concept, nickel here. So 2 plus 1 is what I need. And that's my path length from nickel to currency. And therefore, the similarity between nickel to currency is 1 over 4, which is 0.25. And this you can clearly say that a similarity between nickel and currency is way less than the similarity between the nickel and the coin, which is clear also based on the on their hierarchy in the word net here. Okay, so far we talked about similarity path. There's also something called the word similarity, which is the maximum similarity between C1 and C2 here, which we're not going to focus on mostly in this slide. But here the idea is that a path-based similarity assumes that every edge has the same meaning and every step costs the same, right? So as long as they're within the same the same hierarchy from each other, then we assume that they have the same similarity, just like the case between nickel and coin and fund and budget, right? They're equally the same, although budget is maybe a more generic term than nickel, and fund is also more generic than coin, right? So therefore, it does not really take into consideration here the word rarity or the frequency or generic generic of the words. Okay, so this is kind of wrong. So that's kind of like the main lagging of the WordNet approach, because the higher nodes, like the higher entities or the root nodes, are very abstract. For example, the word book is the most abstract word in the first tree that we of the WordNet here. If you keep going all the way to the leaf node, you'll find section, collection, aggregation, well, which are a niche word and way more specific than the root node, which has a tendency to be the most generic of the WordNet. The the second lagging of this method of using path length on a WordNet is that they're going through abstract concepts, and therefore it should reduce the similarity more. So therefore, we really need some kind of weight across the edges and not some uniform distance, as long as the words have the same path away from the concepts, right? So therefore, there has been some improvements on the WordNet usage of path length, and this improvement is known as information content. A smarter idea is using a probability of concept instead, which is PC as defined in this slide. So the probability of concept is nothing but the probability that a given word belongs to a concept C that we have in our WordNet. So the root node has always a probability of 1, right? So because that's the most probable word in our WordNet. And the lower we go in down the hierarchy, in our WordNet, the probability is getting lower because the words are getting more specific, and so we're getting smaller probabilities. And so that's because specific concepts occur really less frequently in the text than the root nodes. That's the tendency here. Okay, so this is an example of the same WordNet that we're going to add where we're going to add only the probabilities across the edges that relate the concepts together. And so the probability of concept is defined as follows. It's nothing but if you take any probability of a concept in this WordNet, it's equal to the number of words, which is underneath that concept, over n, which is essentially the number of the total number of nodes or the total number of words that we have in our corpus of documents. If you look at this example here in this small screenshot here, so the probability of natural elevation is nothing but 2 over n, which is all the words that we have in this small or number of nodes that we have in this small tree here. Okay, so this is just an example of the same WordNet hierarchy that we just augmented with the probabilities PC from the WordNet. And again, those probabilities here are extracted from a bigger tree, which you cannot see in this slide. But as a toy example, you could see how the probabilities looks like. The lower down the tree you go, you'll see that the probability is getting lower, which means that the word is getting rare because there are way less concepts underneath that node. The most generic node in this tree is, of course, the root node, which happens to be 0.39. And this simply means that that's the most probable word in my word net. Okay, so now how can we, based on this augmented probability, probabilities WordNet, how can we find the similarities between the word? And now we're getting even smarter because in our tree we're giving some weights to the words as we go down the tree. So as you could see, the hill and coast, although they are at the same level of our WordNet, they do not have the same probabilities, just like the case for the prior example when we used only the WordNet using the SIMPAT metric. So the SIMPAT metric does not take into consideration the weights or the importance of the words based on their probabilities, right? Because here, as I said, the fund and budget is equally similar to coin and nickel. So if you look at the same example with probabilities, now coast and shore must have a different similarity score than natural elevation and hill, although they do happen at the same hierarchy in our WordNet. And that's thanks to the weight that we just augmented our WordNet data structure with. So we're going to start with the first Resnick metric. And the Resnick idea is that two words are similar if they share a lot of information. And what do I mean by sharing a lot of information is thanks to this nice metric, LCS, also known as the lowest common subsummer. So here the lowest simply means the most informative common subsummer. It simply means that if I want to find the similarity between two concepts, I need to find what is their their first common parent node, and take the minus log of the the probability of the parent node, which is common between these two concepts. We're going to see that with a nice example in the next slide. Okay, so similarity Resnick between C1 and C2 is equal to minus log of probability of the lowest common subsummer of C1 and C2. And here I'm trying to find the similarity between hill and coast. So hill and coast share the first parent that they share is geological formation, right? So although they do have a direct parent of natural elevation and shore, respectively, they do not share this parent together. So therefore, the lowest common subsummer happens to be geological formation. So the probability of geological formation is equal to 0.00176, which is the probability that have been augmented on the WordNet data structure, and that's what we plug inside of our log function here. So the similarity between the two is nothing but minus log of 0.0176 that we extract from our WordNet augmented. And this is nothing but 2.75. So we can simply say that hill and coast are about 2.75 similarity score, similarity between each other. Now, if I wanted to see how this score is comparing to two other words, such as hill and a natural object, right? So hill and a natural object, which is kind of a far out concept all the way up in the tree, we need to apply the same logic here. So we need to first find what is the lowest common subsummer. And the lowest common subsummer is what is their first parent, which is a parent of both of them, right? So hill have multiple parents, so it has natural elevation, geological formation. The great parent is great grandparent here is natural object, and the first lowest common subsummer is inanimate object, right? So an inanimate object has a probability of 0.167, which we plug inside of our log here, and it's giving us a probability score of 1.77 here. So that's how close the two objects are. So we can clearly say that hill natural object here are less similar than hill and coast, which makes a lot of sense even by the look of the tree and the hierarchies over here. So in other terms, so the similarity used in Resnick takes into consideration not only the hierarchy of the words in the tree, but also their relative importance based on how many words are underneath their structure, right? So how many words are under their umbrella here. Okay, so summary so far. So we talked about two different similarities. One is based on similarity paths on the direct WordNet data structure without any weighting, so which is equal to 1 over the path length of the two concepts. We saw that it has a lot of shortcomings because it does not take into consideration the words that are generic versus the words that are more important and maybe have more information because they do happen way down the tree. And we also saw the second approach of finding similarities between the concepts in our WordNet data structure, which is known as similarity Resnick. So similarity Resnick approach assumes that we have a augmented tree based on the weights that are being added on top of the edges of the tree, and so the similarity is nothing but the minus log of the probability of their longest common subsummer. Okay, so far the WordNet, I should say, these are the teasers based approaches that we're going to talk about. There are other approaches as well, such as Resnick 95, which uses information context in order to evaluate those semantics. There is also 98, information theoretic definition of similarity, and another algorithm known as the LASK algorithm. We're not going into details of those algorithms, but I just want you to know that mostly these are the earliest methods for finding similarity between words, and really to find it does not really find the word in coding itself, but it's able to find how similar are those words based on some data structure. The main limitation of those methods is that if the WordNet does not exist for a language, then of course we should not we cannot use those similarity metrics on this language. And even in English or other languages where the WordNet approaches, it is very highly unlikely to maintain that kind of data structure. So it requires a lot of human in the loop to kind of update the WordNet. So as we're going to see later in this course, the words have a lot of flexibility across the years. So while one word might have some meaning in the 90s, the same word might have a completely different meaning after 1 or 2 decades later on. So so the WordNet also might have missing words, missing senses, or even some incomplete connections. So therefore, this is kind of like a very strong motivation why we should use the second type of methods, which are the more modern methods known as distributional approaches. Okay, so I should start by defining distributional based approaches. And by the definition, distributional based approaches have the word distribution in their title. And here, distribution simply means that if I know the word context in where it lives, right, and the distribution of where it lives, then I should be able to know what's that word meaning. So if two words have the same distribution, they live in the same context, then they probably are related and they are similar, right? So that's the idea behind distributional based methods. So they're based on this Harris hypothesis, or Zelig-Harris 1954 hypothesis, which says that words that occur in similar contexts, they have similar meanings. And here the intuition is that you should know a word by the company it keeps, right? So if A and B, two separate words, have almost the same environments, then they are synonymous here. So and that's way we are able to kind of find the word embedding based on this hypothesis. We're going to see this later. Okay, so this is a direct example of what I'm talking about of the Harris hypothesis. So from sentences like Tesguino makes you drunk, we make Tesguino out of corn. Just based on these sentences, you should be able to infer that probably Tesguino is some kind of alcoholic beverage, right? So there is no dictionary needed based only on the context. You've never heard this word before, but based on the context where it lives, you should be able to kind of deduce what's the meaning of the word, and what are other words that you can use in order to as an alternative of this unknown word here. Okay, why word embeddings? And here the first question that you might ask is, hey, Dr. Filali, why can't we just use a one hot encoding, right? One hot encoding simply means that if you take the Oxford dictionary, right, and you give it for every single word in the dictionary, you just give it an ID, and you represent the words as a sparse vector where you have zeros everywhere and one only in the position of the word in the dictionary, right? So that could be like an idea, a one hot encoding of the words in the dictionary, right? Um, and here it is the main problem of this approach, I should say, is that it is a very extremely sparse vector that we're talking about, and a very highly dimensional vector, right? So how many words do we have in English? Thousands of words. So it means that we are going to have thousands dimensional vector, and where it is sparse, and it is not sparse only in one position. So this is a very much red flag in data mining. We already talked about the curse of dimensionality and how much a dimension costs us a lot when we're doing the mining process, because the distributions are no longer randomly distributed. The data really has this ability to kind of live in the corners of our hyper cube, and no longer being distributed in a uniform way. So therefore, really, what we're looking for in general is just like for the case of graph that we discussed for in Node2Vec and deep walk algorithms. We really want a vector representation of the words in our dictionary. That is, those vectors should be, number one, dense. Number two, mostly they should be highly informative, meaning that they should capture the similarity via distance, cosine angles, or some vector arithmetic, right? So some word representation really should be made using some dense vector representation, and the vector should not be sparse. It should be highly informative and mostly rich in terms of representation. So not a lot of zeros is inside of the vector. Okay, so what is a good word embedding? So these are some classical examples of some word embedding that are represented in 2D or 3D, as you could see in the slide. So if you take the 100 dimensional word embedding that has been mined using the distributional approaches, and just like plotted using plotted after a dimensionality reduction such as t-SNE or PCA here in 2D or 3D, you should be able to see some kind of rules which are indirectly followed by the word embedding, meaning that the distance between man and woman should be more or less equal to the distance between queen and king. Same thing, the distance between walking and walked is almost the same as the swimming and swam. So these are some indirect grammatical rules and word tenses rules that are being followed indirectly by our word embedding algorithm. So the distance between Spain and Madrid is equal to almost equal to distance between Italy and Rome, Germany and Berlin, Turkey and Ankara, Russia and Moscow, etc. So the country's capital's distance based on the vector encodings of those words is mostly similar here. Okay, so what is a word embedding? So word embedding is a mapping from a high-dimensional sparse space, just like I said. If you imagine the Oxford Dictionary, where every word has one in the vector and zero in all the other places in the vector in 100,000 dimensional vector space. Then a good word embedding or a word embedding algorithm is the one that maps it from the high-dimensional sparse space to a low dimensional space, a dense vector space, right? So the low dimensional vector should be ideally in 100 dimensions, and not a lot of zeros are involved. So the main properties of the word embeddings are that the similar words should have similar vectors. So they are being used directly using similarity metrics, and indirectly also as features for some NLP tasks. So if you know the word embedding, I should be able to do a lot of stuff in addition to document classification, document clustering, plagiat detection, but also in the NLP tasks umbrella, we should be able to do stuff like part of speech tagging, right? So if someone is talking, our part of speech tagger is able to, based on the word embedding of all the words that are being spoken, to tag that word as being either as a noun or as a verb or as an adverb. So same thing for name entity recognition. Our recognition algorithm is able to find or recognize the words, the names in our sentences, and kind of tag them as either a person, a time, or an organization here. So text classification is another NLP task, where essentially, if I know what are the most frequent words in my documents, right? Or if I have a document representation based on the word embedding of all the words, an aggregation of word embedding of all the words that we have in our documents, or the top K words that we have in our documents, then I should be able to find what's the most recurrent theme in the document, and classify it as either a food document, a sports document, or a politics document, just based on those vector representation of the words that are inside of those documents. So continuous bayes representation. So distributional bayes models are typically used or categorized into two different categories. So we have, from one hand, account-based models, which are simply just based on the idea of counting the words occurrence in the documents, or counting the vector the vector words or the context words that are in the environment around that particular word, in order to find a representation of that word. We're going to see those methods later, but the idea is that account-based approaches are based on counting, right? So on the other hand, more advanced algorithms are based on prediction based algorithms, such as the ones that are highlighted here. So the word embedding, word-to-vec algorithms are examples of predictive based models, right? So typically we're using a neural network It could be just a shallow neural net. It doesn't have to be a deep deep model, right? Deep learning model. So here we have the Benjua 2003 or the Word2Vec Mikolov from 2013. We also have GLOVE algorithm of 2014. They all rely on the idea that if I know the context of if I'm able to predict what's the next word based on the context, then that kind of give me an idea about what's the word, what's the embedding of that word. So as a byproduct of those algorithms, I'm learning their word embedding, and I'm training the algorithm on predicting what's the next word in a given sentence as a sentence completion kind of task over here. So this is a very smart way of finding word embedding as a byproduct of the task here, which is the prediction task of finding the next word in the sentence. You're going to see that most of those papers are highly impactful. If you just look at those papers in the Google Scholar, you're going to see that they have 100,000 citations by now, because they're kind of like the basis of multiple algorithms so far. So Word2Vec, we're already seeing something similar in the graph modality, which is the Node2Vec algorithm, and it's kind of very similar in terms of spirit. Okay, so continuous representation of words. So here, the information retrieval, we're talking such as the latent space analysis or LSA models and topic modelings. They use documents as context, and so therefore they really capture the semantic relatedness, right? Um, while in the semantic models that uses the words as the context, they capture semantic similarity, right? So which is meaning that they capture boat and ship being similar, and therefore their word embedding is highly similar. While boat and water in the first category of model, such as LSA, here might have similar word vector representations, just based on the fact that they are semantically related here. Okay, so our distributional hypothesis, Harrison 1954. Again, this is just the same example that I've given earlier. The sun is a star, so I already know that sun is a subject, verb is and star is the adjective. So if you just replace here the word sun, the is a star, you kind of have an idea about what kind of alternate words in the dictionary you could use in addition to sun here. So meaning that two words live in the same context if they are semantically similar. Okay, so other classification, we already talked about those, count-based methods versus predictive-based methods. So count-based methods, we're going to talk about them later, are the VSM, vector space models, LSA, singular value SVD or singular value decomposition kind of methods, non-negative matrix factorization. Predictive based models are neural network based, right? So whenever you're using a neural net, then these are within the predictive based model category within the distributional based models. Okay, so the DSM or a word embedding. So I think for the case of the predictive based models, as I mentioned earlier, there is no need for a deep neural network. So if you think about the Word2Vec library, it's using a shallow neural network. Word2Vec has two flavors of the algorithm, either skipgram or continuous bag of words that you're going to see later on. But these are shallow neural networks that are used to train the model to predict what's the next word in a given context. Now, if you ask me, hey, which ones are better? Either distributional based approaches or predictive based approaches or count based approaches within our in our libraries, the answer should be that there is no qualitative difference between those categories. They are all doing the same task, and so they are different in the way they compute the vectors, but they are both means to arrive to the same to the same goal, which is to find the vector encoding of words in the dictionary. Okay, so let's start with our very first model, a vector space model. A vector space model using a term document matrix. Now, assume we have a corpus of documents from D1 to D5, right? So I have multiple documents. And so I want to find the word encodings based on their occurrence in the document. So for the sake of simplicity, let's just say that these are the words that exist in our documents. Data mining is so interesting. Now, if I count the word data in all the documents here, the data might have occurred 40 times in D3, 38 in D4, once in D5, once in D2, and none in D1. So same thing for all the other words that we have in the dictionary. Then we can simply say that the vector representation of the data is 0, 1, 40, 38, and 1. So that way I know that now, based on the documents that I have, data is represented with this short, low dimensional vector, which is kind of dense as well, because I know for sure that data happen sometimes in some documents, and therefore it is in my term document matrix. So remember this matrix word here. So it's known as a term document because the terms are the rows and the documents are the columns. Well, the same thing can be said also about the documents. So the documents are the columns of this matrix, meaning that in addition to the word representation, I do have also a document representation, which is nothing but the vector of occurrences of the words in the same order that they appear in my term documents matrix. Now I can say that D2 is represented as the vector of 1, 5, 2, 6, 1. So why is this interesting? It's interesting because I'm able to find the documents that are mostly similar. I can also find the words that are highly similar just by the fact that they happen in the same documents. So if they happen in the same documents, then most probably they have high tendency to be in documents that have the same theme, and therefore they are highly related in general. Okay, so the vector of word so in this term document matrix is as follows: 4, 6, 0, 4, 25. And that's the word embedding of the word so here. So if I want to compare two words, the word mining and the word so, what I need to do is simply to compare their vectors using some kind of distance or an angle similarity, such as cosine similarity between those two vectors, which is the dot product of those vectors. So and mining are equal. Our equality is measured based on their distance between each other. Okay, so I think I'll stop over here. By now, you should have learned about different ways of finding similarity between words, either using a thesaurus-based approach, which uses a word net as a data structure, or you should also understood that there are two different categories of methods for word embeddings. One, which is based on the count-based approaches, like the vector space model using a term documents matrix. The other one is also based on a predictive model, which we're going to see in the next session. Such as those methods are just like the GLOVE algorithm, the word-to-vec algorithm, which heavily relies on some shallow neural network for finding the next word in a sentence, and that way we are learning those word embeddings in a short in a dense and low dimensional vector here. All right, so I'll stop over here. If you have any questions, please ask that in the next class. Otherwise, good luck with your handout. I hope to see you next time.